Welcome everybody to this afternoon's press conference at 2:15 p.m. Pacific time on Wednesday, June 15th, with the press conference titled Extragalactic Investigations and Evolved Stars. I'll be your MC today. I'm Haley Wahl. I'm the AAS Media Fellow, and I am assisted today by Susanna Kohler, the AAS Press Officer, who will be helping with the in-person Q&A, and Carrie Hensley, the Deputy Press Officer for AAS, who will be assisting with our online portion. There are at least 4 press releases that will be released today, and those will be broadcasted to the AAS press office channels and will also be posted on the Slack and in the press kit. Yesterday and Monday's videos and all of the press things that you will need are in the press kit and that are online. And the one from this morning should be uploaded tonight. So a couple of ground rules. So we are recording this briefing and live streaming it to YouTube as well. I'm going to give a brief introduction to the topic and introduce the panelists and their presentation titles. All the panelists are going to speak in order, and then we'll go to a Q&A. For all the attendees online, if you could please type your questions in the Q&A feature on Zoom. And for everybody, people in the room and people on Zoom, when you have a question, please type or say your affiliate, please indicate your affiliation and who your question is for. And today we are going to talk about extragalactic investigations and evolved stars. And in order, we'll have Valeria Olivares from the University of Kentucky with a presentation titled "Black Hole Activity is Not Evolving in Central Cluster Galaxies." Next up will be Dillon from the California Institute of Technology with the presentation titled "Discovery of an Extremely Luminous, Decades-Old Pulsar Wind Nebula in the Very Large Array Sky Survey." Next, we'll have McCully from Los Cumbres Observatory with a talk titled "Models for the Late Time Excess Flux of a Peculiar Supernova." Next, we'll have Dillon and Plucinsky from the Center for Astrophysics, Harvard and Smithsonian, with a talk titled "A High Velocity Pulsar and a Galactic Supernova Remnant Measured by the Chandra X-ray Observatory." And last but not least, we'll have Ted Johnson from the University of California, Los Angeles, with a talk titled "Strange Abundances in a White Dwarf, Evidence for Simultaneous Accretion of Rocky and Icy Bodies." So I'm going to queue up the first slides and I'll turn it over to the presenters.
So good afternoon to everyone. My name is Valeria Olivares. I'm a postdoc at the University of Kentucky. First of all, I would like to say thank you for giving the opportunity to present this work that I've done with my collaborators. Here I'm showing you some of them. So thanks to Dr. Juan Su and Dr. Paul Nolsen. So in this work, the idea is to understand whether the black hole activities in central cluster galaxies is evolving or not. So first, let's talk about galaxy clusters. Welcome to Galaxy Cluster 101. So we know that galaxy clusters are the most massive system in the entire universe. They have masses of 10 to the 15 solar masses. They contain 100 up to 1,000 of galaxies that are all bound together by gravity. And they are embedded in this sort of diffuse and hot intercluster medium that we can see here in this purple color. So it's turned out that we study clusters a lot with X-ray telescopes. And the reason for that is because those systems have this very hot, diffuse, and very huge gas that have temperatures of 10 million degrees Kelvin. So at this temperature, this gas emits naturally X-ray emission. Okay, so so it turned out that at the center of this galaxy cluster, we find one of the most massive galaxies of the whole universe. There's usually a very massive elliptical, and this is what we call here the central cluster galaxy. Usually these galaxies sit at the bottom of the potential well of these galaxy clusters. Some of these clusters are rapidly losing energy at the center because they are emitting a strong X-ray emission at the very center, and those are called cooling clusters. Okay, so a lot of these central cluster galaxies also have an active black hole. Often these black holes have high speed jets of material, this sort of stretching over 1,000 of light years. So this is in kiloparsecs, between 10 kiloparsecs and 100 kiloparsecs. The cool thing about those radio jets is that they can sort of excavate X-ray cavities, and this is what we are seeing in these images, by sort of pushing aside the surrounding hot gas. So they are actually creating holes or X-ray depression on the intercluster medium. So what I like to argue here is that those features make galaxy cluster the best places to study AGN feedback. And the reason for that is because we can see, and also we can measure the impact that the radio jets have on the surrounding medium. Okay, so to answer our question, is the black hole feedback more common in the early universe than it is today? We need, first of all, we need a representative sample of galaxies that can help us to explore the duty cycle of black hole feedback. This is essentially an estimate of the fraction of systems that have X-ray cavities that are created by these radio jets. So luckily for us, we have the Planck sample of clusters, which is a statistically representative sample of nearby clusters, so clusters that have redshift below 0.35 that are detected over the entire sky. So these samples have about 164 clusters. So we essentially use Chandra observation of this entire sample. I will look for X-ray cavities in the whole intercluster medium. So here I'm showing you an example of those clusters containing X-ray cavities. So as you see here, they have different type of cavities. Some of them have multiple cavities, some of them have single. Also the distribution morphology of those different cavities is very diverse. This is just to tell you how diverse those systems can be. Okay, so to explore whether the black hole activity is evolving with time, we compare our result with a sample of high redshift clusters, so very distant clusters that have been selected with a very similar criteria, and also have the same spatial resolution, about 10 kiloparsecs. So what we find is that that this fraction of X-ray cavities is constant of about 10% over these 8 billion years. So this is we can see here in this plot. So what this result is telling about is that the black hole feedback has not evolved in these central cluster galaxies over these 8 billion years. Okay, so what are the implications of this result? So the interaction between this supermassive black hole and its host galaxy in this cluster, it seems that it had been placed since 8 billion years ago, and since that has not evolved. So as soon as the galaxy cluster relax and start this feedback process, they are able to maintain it over this entire time. So this is open a new door for future high resolution X-ray observations that will be useful to find more cavities in more fainter and more distant clusters at high redshift, in the high redshift universe. And that's it. Thank you. And I leave you here with my contact information. Thanks.
Okay.
Okay, hi everybody, thanks for coming. My name is Dillon Dong, and I'm currently a grad student at Caltech, but I'll be starting as a Jansky Fellow at the National Radio Astronomy Observatory later this year. So today I'm going to tell you a story of this decades-old pulsar wind nebula that we found as a newly appeared source in the radio sky. So this talk is going to be in three parts. First, I'll tell you the story of this nebula. The second, I'm going to tell you about how we pieced together the clues to figure out the story. And in part three, I'm going to zoom out and give you a little bit of the bigger picture. So first of all, our story begins in a galaxy far, far away, or kind of far away, about 400 million light years. In the late 20th century, I'm putting a nominal date here in the bottom right corner of 1990, but there is some uncertainty on that number. So in this galaxy, which is a dwarf galaxy that's forming stars at an extremely rapid rate, there was a massive star that had reached the end of its life. It fused iron all the way into its core, and that core is about to collapse. And in the process of collapsing, in the process of imploding, this core gets crushed into a neutron star, an ultra-dense object that has basically the mass of the sun crammed into the size of a city. And when you cram so much material into such a small space, you amplify the magnetic field, and you have a huge amount of magnetic energy concentrated in this object. And this magnetic energy gets released, and it inflates a bubble within the surrounding gas. This gas at early times is the gas that used to be part of the star. And this is what's called a pulsar wind nebula. And this bubble is inflating. And meanwhile, the star is expanding because it exploded in a supernova. However, at early times, for the first few decades, you're not actually able to see the nebula within. The star guts are basically too dense, and they absorb all of the radio light from inside. So we're not able to see it for the first few decades, but eventually the supernova becomes transparent to radio light as it expands and it dilutes, and this nebula gets revealed from within. And this is what we saw as an emerging radio source in 1998 in an observation of some part of the sky. There was absolutely nothing there. And in 2018, we have a new source. And we were able to piece together the clues to figure out what this new source was. And this is the story that we came up with. So how did we piece together the story? Well, the first thing is that this transient is located in a very unusual location. It's at the center of this dwarf starburst galaxy. This galaxy has about the mass of the Small Magellanic Cloud. It's tiny, but it's forming stars at about 100 times the rate of the Small Magellanic Cloud. This is not very common among galaxies. And this really suggests that whatever this appearing source is associated with a massive star or their remnants. And so you think, well, maybe it's a supernova, right? At least that's what I think at first. But then if you take a look at the actual shape of the radio spectrum, you find something quite unusual. So first of all, it's fading at an extremely slow rate. Over 4 years, it's basically fading at about 5% per year. And second of all, pretty much every explosive source we know has a spectral shape that is pretty steep, illustrated by this red line here, which is not at all like this flat spectrum that we actually observed. And so what could produce such a flat spectrum? Well, you can make a plot here of how luminous something is on the y-axis and how flat or steep the spectrum is on the x-axis. And you see that pretty much every kind of explosive transient we know is on the right side of this plot. And the reason why is because the emission, the radio emission from these transients are accelerated by shocks. And shocks have a theoretical limit that say that they basically have to be on the right side of that line. Whereas our transient is completely on the left side of that line to very high accuracy. So what is on the left side of that line? Well, there are some objects. Pulsar wind nebulae in the galaxy are ubiquitously on the left side of that line. And also these mysterious persistent sources associated with fast radio bursts are also on the left side of the line and also have very similar luminosities to the source that we observed. So this is quite suggestive, but there are theories that these persistent sources associated with fast radio bursts are emerging pulsar wind nebulae, but this hasn't been 100% confirmed yet. And we also have not yet observed any associated fast radio bursts, but we are searching for them. Okay, so zooming out a little bit to the broader context, This is potentially the youngest known pulsar magnetar wind nebula. There have been some claims of the detection of a pulsar wind nebula in supernova 1987A, although this one would be very different because it's far, far more energetic than that source would be. We actually can figure out how old it has to be. It turns out that it's between 14 to 80 years old, which explains several things. One, how luminous it is, and two, why it's fading at a rate that we can actually measure. Pulsar wind nebulae in the galaxy are fading at something like much less than 1% per year. And this actual age, I'm giving 14 to 18 years, but it's really in a 20-year sliding window, starting at 14 years, ending at maybe 60 years for the beginning of that window. And this might be the first glimpse in the radio that of this kind of emerging pulsar wind nebula. And it's not a typical pulsar wind nebula either. We think that the pulsar at the center of it is unusually magnetized for most neutron stars. And this may have to do with why it's so luminous and why we're able to detect it in the first place. So there's two potential mechanisms to power this. It might be magnetic braking of the neutron star's rotation, which is what powers most pulsar wind nebulae in the galaxy. Or it could be the decay of internal strong magnetic fields within the neutron star itself, released potentially through flares. And this is the mechanism that's been proposed for fast radio bursts. So we don't really know which one it is, but whatever it is, it requires an extremely strong magnetic field, much stronger than most neutron stars. And finally, after about 1,000 years, we think that it's going to evolve to some of these higher, like highly magnetized neutron stars or magnetars that we see in the Milky Way. And the last bit of context is that this is actually part of a rapid increase in the detection rate of radio transients that we're finding. Radio transients are emerging radio sources that weren't there before, and they are there now, that we're finding in the Very Large Array Sky Survey. And if you'd like to learn more about what we're finding, please come to my talk on Thursday or send me an email at this email address on your screen. Thank you.
Hello, thank you so much for coming. My name is Curtis McCully. I'm a senior astro data scientist at Las Cumbres Observatory, and today I want to tell you a little bit about a star that survived a supernova. Now, what's a little hard to see in this image up here is a picture of supernova 2012Z. Now, supernova 2012Z was a thermonuclear explosion, which generally marks the complete destruction of a white dwarf star. A white dwarf star being a star that's about the mass of the sun jammed into the size of the Earth. And so generally, since these destroy all of the white dwarf and fully destroy them, we were quite surprised that in 2016, when we went back and we observed this thousands of days after explosion, that the star itself had not been destroyed, but it actually had survived. So what I'm showing you here is I'm showing you a nice Hubble heritage image on the left with different epochs on the right, so different times on the right. So now, and I'll explain these in just a little bit, but so here in this one right here is the supernova when it's bright. Here is what that particular star looked like before it exploded, and here's what it looks like after. And so somehow the star both survived and it is brighter than before the star exploded. So to tell you a little bit about this, I need to go back and I need to talk about a few things about this galaxy and supernovae in general. So type 1a supernovae are extremely important for astronomers as they're tools to measure the cosmic distances as they are standardizable candles. There was a particular type 1a supernova that was in this galaxy. And so this is the normal type of white dwarf supernova that is typically completely destroyed. To follow up on this, deep Hubble images were taken of this between 2005 and 2006. Now, This was very fortuitous for us because it gave us a chance to see the entire life cycle of the supernova from before it exploded to much later after. So this was taken before the supernova exploded. Fast forward to 2012, the supernova 2012Z explodes in the same galaxy where we have Hubble data. And this is a pretty unique opportunity that we have to be able to look for the star that exploded originally. And so we did this, and we did exactly this in 2014. We revisited this site in 2013 after the supernova had faded a little bit, and then we aligned it, and lo and behold, there was a star there. Now, this would be the first time that we've ever been able to see the progenitor system of one of these white dwarf explosions. And so that alone was already very exciting, but we wanted to keep following up. We wanted to know more. So what are we seeing in this image? We're actually seeing a combination of a couple of different things. The way that we make a type 1a supernova is you have some kind of white dwarf, and it has to be stealing material from a companion star, from a binary companion. And so in this case, what we're seeing in these images is we're seeing some combination of material accreting onto this white dwarf and the companion star itself. Fast forward again to more than 1,500 days past explosion, and we were quite surprised to see that the supernova had not gone away. There's still something left over here. And so that's what I'm showing here. So this is the pre-explosion image. You can just barely see the pre-explosion's detection of the star. Here in 2013, you can see where the supernova is, but here, which is when we expected the supernova to be completely gone, it's still much brighter than that top panel. And so when you take the difference of it, there's basically, this is the leftover difference between those two. And just to show that a little bit more quantitatively, to say, well, maybe the supernova has done something strange. Maybe you're just seeing supernova light. Most supernovae we expect to continue fading past this point. So this blue line right here is where the original brightness of the pre-explosion detection is. The supernova itself was very, very bright up here, so many magnitudes brighter. And over time, it faded and faded, and we expected it to follow one of these darker black lines. But however, it didn't seem to do so, and it is flattened out and it stopped fading. So what do we think we're seeing here? Well, we actually think we're seeing a combination of both a central source and the ejected material from the supernova itself in composite. So the supernova, especially as we get towards late time, you see some amount of light from the ejected material, but there's something left over. There is something that is bound together as a leftover part of the explosion. And so this is what we've called a bound remnant. And in some way, these are failed explosions that produce normal, or that do not produce normal type 1a supernova. One of our other major results was that we started to model the light curves of these and the brightnesses of these objects to try and understand how massive the white dwarf was before it exploded. Now, the conventional wisdom has been that type 1a supernovae, these explosions of white dwarfs, happen when they reach about the maximum mass for a white dwarf, which is about 1.4 times the mass of the sun. This is called the Chandrasekhar mass. And for a long time, that's been the assumption. When it reaches that maximum mass, it will then collapse it into a little bit so it can explode. However, our models show that that is not necessarily the case. There's other theoretical models that back this up as well. But the normal type 1a supernovae that we use for cosmological distance indicators are more likely to come from a lower mass white dwarf, something more like 1 times the mass of the sun, so maybe as massive as the sun. Whereas these particular objects all fall around that 1.4 times the mass of the sun, the Chandrasekhar mass limit. And so these objects may constitute what we traditionally thought would produce normal 1As. So that's what I'll leave you with. And my contact information is on the bottom. And so please reach out as you see fit. Thank you.
Okay, good afternoon. I'm Xu Long. I'm postdoc at Center for Astrophysics, Harvard Smithsonian. It's a pleasure to present our work on the first direct measurement of the proper motion of a pulsar in a galactic supernova remnant, G292. Using deep Chandra X-ray Observatory ASI observations from 2006 and 2016, we measure a positional change of 0.21 arcsecond over 10 years baseline at a distance of 20,000 light years. This corresponds to a cake velocity in the plane of sky of 600 kilometers per second, or 1.4 million miles per hour. We directly saw motion of the pulsar in X-ray, something we could only do with Chandra's very sharp region. Because it is so distant, we had to measure the equivalent of the width of a quarter about 50 miles away to see this motion. The pulsar speed is about 30% higher than the previously estimated value. That was based on an indirect method by measuring how far the pulsar is from the center of the explosion. Our mean proper motion implies an age much closer to 2,000 years old, suggesting that G292 might be the remnant of a historical supernova. Unfortunately, the no declination of the remnant means that a historical companion would be below the horizon to Europe, China, and the Middle East. The pulsar we are interested in is associated with a supernova remnant 20,000 light years away from the Earth. The aftermath of the death of a massive star is shown in beautiful detail in this composite image from Chandra. The stellar and circustellar materials are driven out and heated by the shocks. The rapidly expanding shell of gas contains large amounts of elements, such as oxygen in yellow and orange, magnesium in green, and silicon and sulfur in blue. Near the center of the remnant is the so-called Pulsar Nebula, most easily seen in high-energy X-rays. The narrow jet-like feature running from north to the south is parallel to the spin axis of the pulsar. Assuming that the pulsar was born at the center of the remnant, it is thought that recoil from asymmetric explosion may have kicked the pulsar in this direction. Okay. However, the kick direction and the pulsar direction and the pulsar spin direction do not appear to be aligned, in contrast to apparent spin kick alignments seen in some other supernova remnants. So the left panel shows the image of the pulsar observed in 2006, and the right panel is the image of the pulsar in 2016. The cross is the pulsar's position in 2006. We are able to measure such a small shift because we combined Chandra's high-resolution images with careful technique of checking the coordinates of the pulsar and other X-ray sources by using precise position from Gaia satellite. The lower left plot shows the proper motion of the neutron star in G292 lies at the higher end of the distribution of kick velocity for galactic neutron stars. The newly determined speed of the pulsar indicates that G292 and its pulsar may be significantly younger than previously thought. In the lower right panel, the blue ellipse is the extension center of optical ejecta. The magenta cross is the geometrical center of the X-ray emissions. G292 would have exploded about 2,000 years ago as seen from the Earth, rather than 3,000 years ago as previously calculated. Here is a zoomed-in image of the Pulsar Nebula with the direction of motion indicated. The nearly north-south alignment of the jet is misaligned from the kick direction by about 45 degrees. This observed misalignment is consistent with recent results, which demonstrated a similar random distribution of spin kick alignments in 3D simulations of core collapse supernova. There is evidence from X-ray and optical data of G292 that the explosion of the supernova was asymmetric. The image to the right shows Chandra image of silicon ejected in the explosion. There is clearly more silicon in the northwest hemisphere than in the southeast hemisphere. A similar morphology is seen for the other intermediate mass elements and the iron group elements. The arrow in the image shows the direction of motion of the pulsar we have measured. The pulsar is moving in the opposite direction of the ejecta. Simulations show that neutron star can receive a kick velocity up to 1,000 kilometers per second from the recoil due to the conservation of momentum. This picture of an asymmetric distribution of ejecta and a neutron star moving in the opposite direction of the bulk of the ejecta is consistent with the neutrino-driven explosion mechanism for core collapse supernovae. Okay, here is what we have done in this work and with my contact information and the link of our paper. Thank you.
Hi, I'm Ted Johnson. I was an undergrad at UCLA until just a few days ago. And oh, I can't see the presenter view. What do you mean? What? No, it's on.
sorry.
Let me.
Yeah, I thought we renamed it earlier.
I thought so too. Guess it didn't stick.
Perfect. All right. So today I'd like to talk to you about some strange abundances we've detected in a white dwarf that's been polluted by its planetary system. And the interesting model we use to explain these observations that's unlike any models that we have seen before in this field. So first, I would say in a nutshell, we found the first evidence of a white dwarf star that's consuming material from two distinct objects in its planetary system. So let's do a quick refresher on stellar evolution. When stars less than about 8 solar masses run out of fuel, they cast off their outer layers, revealing a hot, dense core. What's left over is called a white dwarf. And these objects are incredibly dense. Their gravity is so high that they have pure hydrogen or helium atmospheres because any heavier elements quickly sink into their interior. However, we still see heavy elements in about 30% of white dwarfs. This means that these stars are consuming or accreting material from their surrounding planetary systems. We can see in this drawing that this planetesimal is too close to its star, and tidal forces are tearing it apart, and a stream of gas and dust is falling onto the star's surface. So let's talk about this incredible planetary laboratory that white dwarfs are. We start with a high resolution spectrum. This one shows absorption from a variety of elements at ultraviolet wavelengths. We compare the spectra to a model and tweak the model until the absorption lines match. From the model, we can infer the chemical composition of the parent material and compare to objects in our solar system. In this figure, we see that a number of white dwarfs are accreting material that is similar in composition to Earth. In general, the compositions of the material we see in white dwarfs are similar to Earth, meteorites, or other objects in the solar system. This is not always the case, though. Let's take a look at these 5 objects. We can see that is the amount of metallic core-forming elements shown here in salmon-colored and dark red increases We also see a decrease in the amount of volatile elements shown here in brown and dark blue. This is generally true, and theories of planetary formation suggest that objects close to their host star tend to be more metal dominated and ice poor, and that bodies that form further out generally have no iron metal and have a significant amount of ices. The material accreting onto the nearby hot white dwarf G238-44, however, does not follow this trend. While it exhibits a significant amount of iron, it is also incredibly carbon and nitrogen rich, elements that form ices. There is no solar system body with these two properties at the same time, and our interpretation is that G238-44 is simultaneously accreting a metallic asteroid with a composition similar to Mercury and an icy exo-Kuiper belt object. The Kuiper belt is a collection of small objects in our solar system similar to the asteroid belt, much further from the sun, beyond the orbits of Neptune and Pluto. These bodies are cold and icy with a small amount of rock and no iron metal. But Mercury, on the other hand, is the closest planet to the sun. It is mostly metallic iron with an outer mantle and crust made up of rocks. We fit two object mixes to our model, to our data, and determine the approximate mass ratios of these objects to be approximately 1 part Kuiper belt object to 1.7 parts Mercury-like asteroid. This is the first time that two distinct objects have been detected accreting onto a white dwarf, and it sheds light into the chaotic nature of these post-main sequence systems. This is an incredibly interesting system to study. It's near, bright, and unusual, leading to our strong and unexpected conclusions. The implications of our two-body model is strong support for theories that post-main sequence systems are chaotic. The once stable orbits of Kuiper belt objects are disturbed enough that they end up close to their star and are ripped apart. It also lends kindly to the possibility of life around other stars. Life as we know it requires rocks and the volatile elements that form ices. Radio telescopes such as ALMA have detected belts around young stars that are far enough out to be Kuiper belts, but this is the first chemical evidence that both icy and rocky belts are formed in the same systems. So, thank you, and I look forward to your questions.
Alrighty, so we are going to begin the Q&A. A quick reminder, a couple of quick reminders that if you have a question, please, before you ask the question, state your affiliation and who your question is for. And for those online, please put your question in the Q&A box. And please, if you ask a question, do not remove your mask. You can hear just fine in the microphone, so keeping everybody safe. Okay, I think you're on room Q&A.
Oh, I am. You're right.
Yeah.
Okay. Well,
Do you have any questions online? Okay, we'll start with the online question.
Yeah, we can go ahead with this question here and then we'll move to the folks in the room. I have a question for Curtis from Rick Lovett, freelancer. What is it that caused this one supernova not to fully explode? And how does that relate to the mass models you were discussing at the end of your presentation?
Yeah, that's a great question. Yeah, we think it has to do with how fast the burning moves through the star. So if the burning through the star detonates the star, it's more likely to produce something that fully unbinds it. Whereas if there's a lot of turbulence, then it won't necessarily be able to fully destroy the star.
Hi, this is Ethan Siegel from Start to the Bang. This question is also from Curtis. I'm a little surprised that you concluded that this was some sort of incomplete supernova, given that it was a type 1A. Rather than being some sort of remnant of a 1A, could this have been an accretion-driven type 1A supernova? where the companion star has simply survived, possibly obtaining a greater brightness than original due to some sort of star supernova interaction?
Yeah, again, a very good question. This is one of the models we checked, and based on the pre-explosion images and the constraints from that, we found that the companion star wouldn't be bright enough yet to explain what we saw in our early data, or in this most recent data. As things go, maybe in the next 10 years, the companion star may become the dominant energy source of what's left over.
This is Govert Schilling, freelance from the Netherlands, with a question for Ted. You said the object that plunges into this white dwarf does not have a solar system analog. But we also know that the solar system is not very typical with all the extra solar planetary systems. So could this be one of these super Earth or mini Neptune worlds that have a combination of rocks and ice?
So one of the analysis techniques that we undertook in the paper is to do what's called an oxygen budget, where we match up all the oxygen with magnesium, silicon, iron to form rocks and see what's left over. And then generally, if there's oxygen left over, you have ice. If there's not enough oxygen, you have iron metal. We found that the composition we see accreting onto this star requires both iron metal and water ice. But we know that there's water ice because there's a lot of carbon and nitrogen which form with ices. So the material has to be both metal rich and ice rich, and those two things just don't form together in a single object according to current theories of planetary formation.
Other questions?
Over here.
Hi, this is Bill Grunenberg. I'm with Griffith Observatory. And Ted, the two objects, is there any way we'll be able to identify them in any wavelength? Or the accretion, the streams of accretion?
As far as I know, not currently.
Just too small?
But I am not an expert in imaging these kinds of systems at all.
Okay. All right. Thank you.
I have a question for Curtis. This one comes from me, Carrie Hensley of the AAS. I think this question is going to reveal my ignorance of the physical properties of white dwarfs, but I'm going to go ahead and ask it anyway. I know that supernovae do not necessarily explode in a way that is perfectly spherically symmetric. Is there a chance that this event could have imparted significant asymmetry to the remnant? And if so, how long would that stick around? And is that something you could test observationally?
Yeah, no, asymmetry in supernovae is definitely a very important topic of study. In general, these show pretty low asymmetry, so we don't expect to say jets. And so they are mostly spherical. The exact constraints are quite difficult because they require polarimetry. That being said, the timescales to keep those in place are usually pretty small, especially for the bound remnant.
Great, thank you.
Any other questions in the room or online?
Hi, I'm Katya Fosdick. I just graduated from UW-Madison, and I had a question for Dillon. Yeah, so I was wondering, the photo that you show of the object in your talk, was that like an actual optical image of it, or is that just like an example that you found?
So are you talking about the 1998 to 2018 comparison?
Yeah,
Those
I think
are,
so.
So the 1998 image comes from a survey called FIRST that was done by the VLA in the 90s. And the 2018 image comes from the VLA Sky Survey. So they're both radio images.
Okay.
Any other questions?
All right, if there aren't further, I think we can end a few minutes early.
All righty. So let's give the speakers a hand one more time. I just wanted to thank the audience for your attention. Thank you to the public information officers who helped with the press releases and with briefing prep. Thank you to USRA and our sponsors. The next press conference, the last one of AAS 240, is tomorrow at 10:15 a.m. Pacific time, titled Dusty Environments Near and Far. So I hope to see you there.